Alrighty, y'all, today I'm taking a look at question number 2 from Recitation 10. And for this one, we're going to be finding out how much work is done by a Coulomb force. So I'm just going to start with our general definition for work, which is the integral of our force dotted with this dr vector, and that's evaluated from R1 to R2, our starting point and our ending point. So for this situation, we have our proton here, and we have an electron being brought in from infinitely far away to this radius of 0.529 times 10 to the negative 10th meters. So if we look, I don't want to have to deal with like the vectors and all that for the integral. So if we look at our electric force, right, since these are opposite charges, the electric force that this proton will have on the electron is going to be, it's going to go this way. It's going to be an attraction force. And our radius, we're going to set, if we set this proton as our origin, because we have our R2 of infinity and our R1 of 0.529 times 10 to the negative 10th meters, our R vectors are both going to be going this direction. But the point is they're going to be parallel. So if we end up dotting these two things together, our F direction dotted with our R direction is going to just give us the magnitudes of them multiplied together. But since they're going in opposite directions, we're just going to multiply by -1. Because again, if it would be like the magnitudes of each times the cosine of the angle between them. It's going to be like cosine of pi, which is -1. So that's the calculus there. Not even calculus. We went over that in my calculus class, but so now we can start finding all these things. So our force for this one is going to be the electric force between the two, the proton and the electron. So it's going to be our work is the integral of our, and then the force between them is just going to be our Coulomb's law. It's going to be Q1, Q2, all over R squared, times, and like I said, it's just going to be the magnitude of that. So it's going to be, well, it's not dotted anymore because it's not vectors, but it's going to be times dr. When we're evaluating this, we're starting at infinity, and we're bringing it to this other point, 0.529 times 10 to the negative 10th. Again, we're keeping everything in meters, so we keep it in consistent units for the end, and we can get an answer that is in units that make sense. And this is also all times -1, because again, we have that -1 from that dot product because they're going in opposite directions. So now I don't want to take this integral because it kind of looks like a mess. So I'm going to start pulling out some of the constants to make it a little bit easier. So this entire top part, this entire numerator is all constant, and then also the -1 we can pull out as well. So that's going to give us a negative KE Q1, Q2 times the integral from infinity to 0.529 times 10 to the negative 10th of dr over r squared. Now this is a bit simpler of an integral. So this we can remember from our calculus class that we have, this is now r to the -2 dr. We're taking the integral. So if we're integrating that with respect to r, that's just going to be r to the -1. And that's going to be negative because, again, if we take the derivative, we multiply by that -1. And we're evaluating, again, from infinity to 0.529 times 10 to the negative 10th. So if I plug this all back into what we have over here, we're going to get KE Q1 Q2 times, because again I dropped this negative because I multiplied in by this negative. That's all that was, times 1 over r, but r is going to be evaluated between infinity and 0.529 times 10 to the negative 10th. That's a long number. But now this is just, we can take the limit as it approaches infinity instead of just plugging it in, because infinity is not a number that you can just plug in. So if I start plugging in the values, we have KE Our Q1, I'm just going to say is the proton. Why not? 1.602 times 10 to the negative 19th. And then multiplied that by the charge of the electron, which is negative 1.602 times 10 to the negative 19th. And then that whole mass is going to be multiplied by this whole mass. So we're just going to plug that in. It's going to be 1 over 0.529 times 10 to the negative 10th minus, and again, we have to take the limit because infinity is not a real number. P, doesn't matter what the variable is, just taking the limit of it. Really, that's just to say that 1 over a really big number is going to go to 0. So that's just going to go away. And then we're going to end up with KE. I don't feel like writing this out twice, so I'm going to take this negative, put it out front over here, and just say it's this value squared because they're the same value at that point once I get rid of that negative. 1.602 times 10 to the negative 19th squared, and that's all going to be divided by this radius over here, because again, that was our R2. It's going to be 0.529 times 10 to the negative 10th. So this is going to give us our answer, and again, if we plug in, we have to plug in KE is 8.99 times 10 to the 9th. But this is going to give us for the work done by the Coulomb force, but the original question asks how much work, so that would just be the magnitude of this, so we can get rid of that negative sign, and it's just going to be KE times 1.602 times 10 to the negative 19th squared all over 0.529 times 10 to the negative 10th. And again, you can plug this into your calculator and get your final answer for that. All right. Hi. Well, I hope you have found this helpful at all. Let me know if you have any more questions or if there's any other problems that you want me to try to explain, because I guess Sydney explains stuff.